All right, welcome back, everyone. Congratulations for the amazing work during this intense day and a half. And our judges are really looking forward to seeing all of your contributions during this hackathon. We know it has been intense, but hang in there. We still have two amazing speakers. And after that, we're going to announce the 5 winning teams and do a little celebration here. Okay, so I'm going to introduce you to our first speaker, Léonard Boussioux. So Léonard is an assistant professor in the Department of Information Systems and Operations Management at the University of Washington, Foster Business School. He completed his PhD in operations research at the MIT, working with Professor Bert Simas. His research bridges operations research with machine learning and AI, emphasizing multimodal frameworks and data-driven decision tools. He aims to tackle critical healthcare and sustainability challenges by developing robust, explainable models that harness the power of cutting-edge predictive and prescriptive analytics. He's also working on pushing the boundaries of creativity and innovation using generative AI. And outside of MIT, he has a diversified experience as he interned at Google X, the Moonshot Factory, to advance biodiversity monitoring and ecosystem modeling. He was also a research intern here at Mila, advised by Professor Yoshua Benjo, and he was a visiting scholar at the Center for Entrepreneurship and Technology at UC Berkeley. We're very happy to have you here with us, Léonard, and thank you for being here. The floor is yours.
Thanks so much for the kind introduction. I'm super delighted to be here today, and I will talk more about how we can use AI and operations research to tackle complex problems around sustainability. And as you mentioned, I was actually indeed a research intern 5 years ago. I mean, this is how I kickstarted my career in AI, and I'm so grateful for the amazing time I had at Mila. After that, I really wanted to start a PhD, and I liked academia so much that I decided to become a professor. So all of this started when I was at Mila, and really I had an amazing time there, and I learned so much for all my future career. So today, I will talk more about how we can merge different concepts from operations research and AI so that we can go towards decision making. And in particular, I was delighted that at Mila I could learn a lot about AI, but then I complemented my education at MIT with the field of operations research, which consists in using, in particular, optimization to go towards decision making. So it was very useful to actually determine how to prescribe actions, which is more than just predicting a few different possible outcomes. So today I will want to talk more about the concept of multimodality. And I actually discovered that when I was at Mila, because I was working on a project called Baby AI, where we wanted to understand how we could give instructions to an agent in an environment so that the agent could do a few actions. And this concept, I found it to be, in fact, extremely interesting for a lot of real-world problems. So I will show how we can use multimodality with, in particular, an application to hurricane forecasting. And finally, I will talk more with the remaining time about how we can use robust optimization, which is a sub-branch of optimization, focusing on how to take into account uncertainty for the concept of time series forecasting, which is in fact quite challenging. So without further ado, I will now move towards the multimodality. So I am sure that many of you have heard about it, or maybe likely even working on this, and especially with a challenge around natural disaster management, multimodality is very important. So overall, multimodality is this capacity to process, relate, and have multiple information from multiple data sources that we are going to merge and inform together. For instance, tables, time series, sound, images. And as you know, this is quite challenging to process all of that because they're all in very different formats. And the idea is, how can we replicate our natural cognitive process to assist decision making? Because as humans, we are constantly every day making tons of decisions, taking so many different things into account. So how can we combine all of this into algorithms? And that's a challenging question. And for example, in healthcare, multimodality is extremely important. If you go and see a doctor, they will ask tons of information about you. So for instance, gender, weight, blood pressure. They will have maybe electrocardiograms about you, X-ray, MRI pictures, CAT scans. Nurses and doctors will write notes. So if you go to a hospital, they will try to take every information about you into account to make a diagnosis or prescribe something. So if we want to do an AI to help doctors, we may need to be able to process all those informations. And for example, also with weather forecasting, we look at the forecasts very often, especially their hurricanes. To predict weather, we look at a lot of different data sources. So we have different weather stations, radar stations. They collect, for instance, time series. They also have can be infrared. It can be just pure pictures. So to merge all of this is very complex. So how to combine the modalities? So I'm sure that many of you also have played with different things. Overall, I just want to mention two simplified workflows. One is using end-to-end models, where you're going to have a master massive model that will look into all the modalities at the same time. And you may have different parts of your, for instance, neural network that will process them. But overall, you have one big back propagation for everything at the same time. And finally, you can make a prediction, for instance. Another way that I really like is also to extract features out of each modality. In particular, for instance, you can extract features from your time series, features from your images, features from your text. And then you're going to combine the embeddings, meaning the features extracted out of each modality, and you combine them into, for instance, a final predictive model. It can be, for instance, a tree-based model like XGBoost. So if we look into the end-to-end models, the nice thing is that all modalities are going to interact together within the same overall architecture. So you can have the whole training with one back propagation, for instance. The inconvenience is that it's not very modular or generalizable. And you need a lot of data in general. It's very sensitive to noise. It's difficult to debug code, etc. And it's not necessarily easy to interpret or explain how the decisions are made. However, I also know that, of course, such models can be extremely promising in the future. And then, for instance, ChatGPT-4, they've been trying to train it on many modalities. Many companies are working on this. So it's also definitely the future, but not necessarily easy if you're just a student working in a small research group. You don't have all the capacities. So this is why I also appreciate the capacity to extract features. And then you can leverage transfer learning, zero-shot learning, reuse all the models, for instance, from Hugging Face and many other repositories that have been trained on massive amount of data. And then you can just reuse them for a specific new use case for you, and you extract features like that. Of course, the challenge is how to extract the right features, and this is, of course, an interesting research direction. Also, the modalities don't interact the same way. They interact at the feature and the embedded stage, and not anymore overall in the same overall architecture. So I like to leverage many transfer learning, zero-shot learning. Like you all know about all those brilliant models and architectures. Overall, what I want to say is I find super useful to be able to reuse models trained by the community for a new use case. And then feature extraction in that case can be extremely helpful for tackling new problems that were not specifically trained with the previous model. So overall, what I will talk more today is about this recipe that I call collect, extract, predict, where you collect your different data sources and you are going to try to align them. And then you're going to extract features out of each one of the modalities. And then you are going to take all those features extracted within a final predictive or prescriptive model to get the output that you care about. And during my PhD thesis at MIT, I've actually used this methodology for a lot of use cases, in particular tropical cyclone forecasting, ecosystem conservation to understand better how different species are going to be more or less in a given environment, and finally also healthcare to help a lot of doctors making better diagnoses. So now I'm going to talk more about how we can use such framework for tropical cyclone forecasting. So this is based on joint work with my friend Cynthia, Theo, and my advisor, Dimitris Bertsima. This is work that I performed during my PhD at MIT. So what was interesting also is that none of us had any background in weather. So we did not know more about weather than you likely know now. And then we decided to tackle this very difficult problem. And a few lessons I learned is that help us being more creative what the community of weather forecasting would have done. How we also had a lack of knowledge that was sometimes crucial to actually do the exact research that was needed. So the process to get this published into the a very good weather journal, the Weather and Forecasting, which is exactly specialized in this specific topic, was very long. We had a lot of reviews from reviewers, high quality reviews, and then they were very much specialists, of course, and they knew we were not. So I learned a lot from this, that it's actually nice to have someone in your team who is from this exact field that you care about, and you may avoid a lot of tiny mistakes that in fact are very huge in the end and will take more of the time and may limit your impact. So in the future, that's really a takeaway for me whenever I want to tackle something very specific for a specific topic. So let's say with some motivation, you've all heard about the hurricane recently in Libya. There is currently the Hurricane Lee. I know that you had a talk earlier that mentioned those hurricanes. So you can see hurricanes every year. It's a huge mess for many countries. And the one I'm mentioning here, Hurricane Ian, is from last year. And it was really one of the deadliest and costliest of the history in the United States. And in particular, the problem was that this hurricane was extremely hard to forecast. And there was a lot of poor decision-making and evacuation orders on the ground. So hurricanes, they draw their energy from warm ocean waters. So what's happening is that this is why they're called tropical cyclones. They are going to get all this energy from the waters. They are going to form and start turning, and they go westwards very often. And then they go from a stage of tropical storm towards finally a hurricane. So if they become strong enough, they become hurricanes. And then they get a name also. So fun fact, the hurricanes are getting the same names every 4 years. So there is a rotation. But if one is so deadly and so such a disaster, they remove the name forever because it has a lot of impact on people's minds. So for instance, Hurricane Katrina, that was very sadly famous. There will never be another Hurricane Katrina. So today, I'm interested in predicting the stage where the hurricanes started already to form into a very strong tropical depression, and then are going potentially to wreak havoc on land. There are several tasks that are very important. The first one is the track. You want to know where the hurricane is going to go. But there is also the intensity. You want to know how intense, how strong the winds are going to be, because this is very important, in particular, to determine the storm surge. What happens is the effect of intensity, meaning how strong the winds are, will have a direct impact on how much there will be floods. And this is what triggers, for instance, evacuation warning or not. It turns out that deaths during hurricanes are to the storm surge, not necessarily to the high winds. It's because people don't evacuate or stay home, they get stuck, or they try to evacuate too late, and then the car gets carried away. So this is why it's very important to predict the intensity. And this is what is, in fact, one of the most important tasks. Also, a very fun fact, this kind of graphic is what is communicated on the ground for evacuation orders. It turns out that there is a cone of uncertainty. You can see like this white shaded area. In fact, this white shaded area is the same for all hurricanes. So this is very misleading. This is just based on the statistical errors from the past 5 years. And it's not hurricane specific. And a lot of people believe that if they're not on this cone of uncertainty, then they're good and they're safe. And this is why, for sure, there is more to do around visualization and the importance of showing properly how a hurricane is going to behave. So our goal today will be to advance hurricane forecasting using multimodal machine learning. And we have the publicly available data of all tropical cyclones in the past 40 years, which means that it is not an immense data set, but it's large enough to be able to train typical deep learning models. And as you can see, there are hurricanes in the whole world, and they're divided into basins. For instance, the North Atlantic Basin is the one that is of interest, for instance, with the Hurricane Lee right now. And then there is also, of course, the Western Pacific and many others. The hurricane that hit in Libya was not exactly the same kind of a tropical cyclone. It's a similar phenomenon, but it formed a bit differently too. So I'm going to use all of this data to make multimodal machine learning happen. So why am I talking about multimodal data? Because we are going to use several data sources. First of all, we can collect historical storm features. So this is again publicly available. For every hurricane in the past, we know where the center moved, and we have a few very important weather features, such as the geolocation, the storm direction, how fast it goes, pressure, and many other features. So I'm going to use those, and this is a time series. I also have access to reanalysis maps, meaning some calculated data about the wind speed, the pressure at different altitude levels for each hurricane. So it's a map that is also a time series because I have the evolution of this map across time. And I also have that at different altitude levels, which is very crucial to being able to predict a storm because the storm behaves differently at different altitude levels. And finally, we also want to compare the performance of our new models with the actual models used by the National Hurricane Center for the United States and Northern and Canada. So we have access to their forecasts, and we are going to compare the performance. So the key results from the study are the following. We were able to build a successful feature extraction method that also brought new perspective to the meteorological and earth science field. So before there was no such publication in this field. So we managed to get it published in a weather journal, which actually helped this community seeing other benefits. It turns out that the weather community is not necessarily looking a lot at all the computer science AI conferences, and they care more about what gets published in their journals. So that's also sometimes it's very often the case for specific fields that we need to try to publish in their things to influence them. The top models that so the second takeaway is that the top models that we managed to build had a comparable performance with the best National Hurricane Center models, which is very nice for deep learning because the models developed by the National Hurricane Center are based on decades of research. And I think that in the earlier talk today, you learned more about the dynamical models, statistical dynamical models that are mostly based on equations. So equations, for instance, with Navier-Stokes, where they're going to try to model the whole atmosphere. So deep learning is data-driven here. And finally, if we include our models into a consensus model and using robust optimization, we managed to improve the performance of the official forecast by 520%. So here, what it means is, if we include our model as one more model that they can use, this is going to improve overall their performance for the National Hurricane Center. And in fact, the predictions are not made solely by one model. They use a collection of many models to improve the performance. It's called ensemble modeling as well. So here is how we made it happen. Overall, we had, as I mentioned, the time series of images. So the time series of those reanalysis maps at different altitude levels. And we also had the time series that is more sparse, meaning we have the location of the center and a few important features. Then we are going to use deep learning to extract features. So we built what I call vision embeddings out of this visual data. I'm going to process also the time series on their own. I'm going to concatenate all those features together. I will input this into a gradient boosted tree, like XGBoost in our case. And then we are going to train this final XGBoost model to predict the intensity and the track of a given hurricane. So here, what I'm going to focus now is quickly explaining how we extracted the features. So the way it works is the following. Imagine you have a hurricane right now, like there is one, there is Hurricane Lee. I'm going to look at the previous maps. So the ones from the past 24 hours, for instance. And then I will input this into a convolutional neural network. I will also add the statistical data, meaning this is the extra metadata and information I have about this specific point in time. I concatenate them, and I push this into a transformer. And finally, I have a fully connected layer for the prediction. Notice that what we wanted initially from that was feature extraction. And then you still need to train this whole architecture. And then we cannot train it in an unsupervised fashion. So we are going to just actually ask to predict the intensity and the track directly with this overall deep learning architecture. Like this, we have a supervised signal. And then I'm going to extract features out of the last layer of the transformer. So I'm going to use the features after I froze this overall architecture as new features that will hopefully embed most of the information from all my maps. And then I'm back here where I can have, therefore, my vision embeddings. So overall, a few results. End-to-end deep learning, meaning this overall architecture with CNN plus transformer. If we ask to predict directly the hurricanes, it is not as good as after extracting those features and recombining them with XGBoost. So it's interesting that extracting the features plus recombining them plus XGBoost is actually slightly better. And then we can compare the performance of this feature extraction method with the best models from the NHC. So the best statistical dynamical model, meaning a model that is based on, in particular, simple regression that uses different features. And then the best dynamical model, this one is called the American model, where they are going to use dynamical equations. So we have a very competitive performance compared to the top NHC models. So overall, this method was very modular and general. You can collect your data, extracting the features, and make predictions. I focus here so far on predictions. You could also prescribe, meaning advise on an action. However, to advise on an action, it's interesting to use optimization, for instance, mixed integer optimization, linear optimization. And then there were a lot of extensions and more work done. So it's really an active topic to forecast hurricanes, cyclones, and weather using machine learning. And then I used, again, this same method of extracting features, recombining them for many use cases, and it's always been successful. And I want to mention, of course, that I don't necessarily have massive amount of data. This is why feature extraction actually came up super useful for us. And the models we built, we actually deployed them at the Montreal Insectarium for the ecosystem conservation, and then also in hospitals, in particular in Boston and Hartford, which is in Connecticut. So overall, as you know, from this hackathon, satellite data can help advance sustainable development very fast because you have access to data from all over the world with a low cost, it's high spatial resolution. So the talk after me by Lydia will talk more about all of that. And then I'm currently investigating way more topics around natural disaster management, how to do forestry conservation, precise agriculture. I find it super exciting that we have a mine of information, we have amazing tools, and then I focus on how I can also use optimization to prescribe and advise in a very personalized way how to make such decisions. Now I want to briefly talk about another concept, which is ensemble modeling. So as you could see, we have hurricanes. However, sometimes even the best models are going to fail to forecast what is called a rapid intensification, meaning a hurricane that suddenly intensifies enormously in 24 hours. Those are very dangerous because it means that you are not ready for it and you did not issue the evacuation orders. And in fact, it's the worst forecaster nightmare that you go to bed and you wake up in the morning with a massive hurricane. And it turns out that even the best models, they can fail. So I give you an example from 2018 that really was a big issue, where suddenly in one day, the hurricane went from category 3 to 5. Hurricane category 5 is massive. And these are all the models. They all failed to forecast the rapid intensification, including the deep learning model we had built ourselves. And the official forecast issued by the NHC, of course, missed it because it's a consensus model, which is sort of an average of all the models they have available. So if you average models that are all faulty, you will likely end up with a faulty model again. So this is everything that was missed. However, using robust optimization, we managed to catch this rapid intensification case, because the concept of robust optimization is to being robust against uncertainty and being robust against what you cannot a priori predict, but can be within a given range of things, of scenarios that are possible. So this is based on joint work with my advisor. I won't talk about the maps too much. I mean, I won't have time to cover this, but it's actually super interesting to see how we can use optimization and robust optimization to take into account uncertainty. Briefly summarize what is ensemble modeling. Everybody likely knows about that, but it's in fact super powerful. And in many use cases, it's actually used in the real world. So the principle is the following. You start with your data. You are going to use different base learners. It can be XGBoost, a decision tree, a random forest, a neural network, a transformer. You have different, therefore, predictions. And you're going to take all those predictions and give them into what is called an ensemble model. So the ensemble model can be just an average. It can be the median. It can be a more sophisticated one, like for instance, just a simple linear regression. It can be more sophisticated. There is the whole field of mixture of experts. And then you get your final prediction. So this is what we did. We developed another kind of ensemble model that could adapt with time series, because time series are also a bit more challenging, because you have a lot of issues with data drift and model drift. So the models can change maybe across time. The data can change across time. So how to account for all those variations, the robust optimization field is very, very interesting. And we applied this for the case of hurricane forecasting, but also air pollution management. We actually deployed a model for air pollution management in the city of Safi in Morocco, where we helped the company OCP to being able to better determine when they should pollute or not, because they cannot avoid polluting when they produce a lot of phosphates, which is one of the biggest productions of OCP in Morocco. So to help them, we told them when is the best time to pollute, such that your pollution won't go to the nearby city, but instead will go in the ocean. It's imperfect, of course. You wish you could not pollute, but they have to for the production. So we used robust optimization to help them determine when the weather would not be the best. And of course, and we can also use this for electricity. And those time series are all very different. So this is why it's interesting to have different, a nice framework to being able to understand the uncertainty of many different kinds of time series. Some of them are seasonal, some of them are daily, some of them have sudden peaks. So robust optimization has different uncertainty sets to deal with all. Can you hear me in the room?
Yes, all good. It disconnected for 5 seconds.
Yeah, so I was saying that like there are many famous methods for ensembling. For instance, bagging with the random forest, boosting with XGBoost, and stacking where you just take different models. All of those are highly studied and super impactful. And then I will quickly skip the results, but overall the key takeaway is if you use robust optimization plus all the models of the NHC plus the our deep learning model, we have really a better performance by up to 20%. So really having AI models plus traditional models, because the deep learning models are able to capture something different than the usual NHC, because it's more data driven. So there is a lot of future to be done there. And using robust optimization is able to recorrect a few mistakes of all the models together. So overall, the key takeaways from my talk are that multimodality has a huge promise. And then, of course, foundation models can be super, super helpful. Like IBM just released a foundation model for satellite imagery, but you don't necessarily have access to those models You don't necessarily have access to the resources to retrain your own. So I think that using feature extraction can be a good help if you are dealing with a difficult specific problem, if you don't have necessarily all the resources, if it's hard for you to actually have a whole software engineering team. And this can really enable deploying the next generation of models very fast. And it's very interdisciplinary. And I also highly recommend looking into the field of operations research and optimization, because it can deal with uncertainty, decision-making, and machine learning is not necessarily the only answer to actually make decisions. Using optimization, mixed integer optimization is super helpful. So if you have a chance to take a course on this, I really recommend it. And I want to finish by mentioning also the value of just educating so many crowds about the beauty of using all those tools. So at MIT, I was teaching a course around AI and optimization for a better world. And we taught this to undergrad students. And what I noticed is that I actually forced the students to use ChatGPT to answer a lot of questions. And I built all the assignments and projects with the help of ChatGPT, asked them to use this. And of course, in a smart way. It turns out that this year with ChatGPT, the students have never been that good. Many of them tackled challenges around satellite imagery, and no students had ever done this before because it was considered too hard, and we did not have the time in one semester to teach all of this. And these days, I'm also super excited about this provocative title, that how can we solve the United Nations Sustainable Development Goals in just 5 minutes? So my dream is that we can use generative AI, guide it, help a lot of new students, young populations, people who are not trained, to actually solve the problems they care about. And I just want to give you in one little example of why I consider this to be very interesting. Let's say you want to do something around sustainable cities and communities, and I ask you in 1 second to suddenly think about what you could do. In 1 second, it's very hard for us. However, when you take AI, you have the capacity to quickly generate visuals, for instance, quickly iterate and being extremely creative. So I really believe that this is through the combination of human AI, generative AI, that we can accelerate our progress towards sustainable development goals. And I want to mention that we have a shortage of 3.5 million of data scientists that are needed by low and middle income countries to help for social impact. And finally, to conclude, these days it's my latest work where I investigate the quality of AI-generated solutions to difficult challenges, in particular around circular economy. And it turns out that the idea quality between humans and AI was similar. The trade-off is that the human ideas are actually more novel, but GPT-4 was able to deliver more value, meaning it's better to understand how I can bring financial and environmental impact. So I think there are so many synergies that are coming, and we are really in an amazing spot, all of us, to make a lot of cool things happen for a better world. So I'm very grateful to have this opportunity to talk with you today, and I'm super delighted to take more questions and being in touch in the future. Thank you.
Thank you so much, Léonard. That was a very, very inspiring talk. Okay, so we'll start with the questions from the audience first. Okay, we'll start with the audience and then us.
Hello.
Hey.
First of all, thank you, Léonard, for the amazing presentation. I mean, it was so insightful. I think I speak for everyone here. I was personally amazed with the work. I'm not the best person in AI. Actually, I'm a little bit far from this domain. But my question is related to the last point you mentioned, which is dreaming of what could happen in the future. So my question is, can we dream of a day where we can predict with the best accuracy hurricanes or other disasters to a point where we can actually avoid them and act in advance to avoid the casualties and everything that come with them?
Thank you for the question. So what I can say is even though we are able to make amazing predictions, there is still a lot of human aspects. And the reason why a lot of people are dying because of hurricanes is because they decide to not evacuate, or even if you ask them to do so. And it's actually quite funny, for instance, for the United States, it's very political. It turns out that in some areas, for instance, in Florida, if you are like a Republican would decide sometimes to not say to order, because they don't want to hurt the feelings of people who would think, look, I've been living here forever. I've never died. I've always survived hurricanes. Why would this one be any different? It turns out that this is the kind of behavior that can trigger like a sudden death. So here it's not necessarily about having the best models. It's also about dealing with all the human emotions. If we are able to predict better, we're able to give recommendations that are better, but we are not necessarily able to really help the people on the ground. And I believe that this is why it's even more than just having models. We'll have so much more progress to do in terms of actual politics to incentivize people to go out or prepare areas so that they can survive the hurricanes. But in terms of accuracy, I really see the progress, like there is constant progress being made. And then there are a lot of methods now around how to merge deep learning with actual dynamical models, meaning it's the combination of the power of two fields, machine learning field and weather field.
Can you hear me? Yeah, okay. Hi. Thank you for your presentation. I really like that you used ChatGPT in your course. I think a few decades ago, people were saying that you shouldn't look for any information on the internet. It's not trustworthy. And 10 years after that, it was Wikipedia. And these days it's, generative AI, ChatGPT. So I think it's where the world is going. And so we need to learn how to use it instead of pretending it's not there. So I guess my question is, what would be your main takeaways using this in your course? How do you use ChatGPT in a smart way, especially as an educator, not just as as an individual, but how did you design the questions, and how did you help them understand how to use it, what it's good at and what it's not good at? Thank you.
Thank you. I'm actually super passionate about this question because I think education has a tremendous role to increase the happiness in the world and what we can solve. So when I started the course, it was in February, meaning ChatGPT just came out. And then it turns out that actually many classes at MIT, the professors forbid the students to use ChatGPT. And as a result, my students were not very reluctant to use it. I was really forcing them, and many of them had used it for the first time within the course. So considering this, people were not trusting in the model that much, I actually asked questions that were within the realm of what ChatGPT can do and outside of the realm. I give you a simple example. If it's about brainstorming, ChatGPT is very good. If it's about solving an optimization problem, it can really hallucinate an answer. And my students did not know at all about linear optimization when they started the course. So I actually asked them to use ChatGPT to solve linear optimization, mixed integer optimization. It turns out that half the class blindly trusted the answers just because they looked really good, although I triggered them in the question to double check everything. And then ChatGPT just hallucinated something that is completely wrong. And if you do just a quick check, you will see it's very obvious. And this was a big lesson for the students. They actually learned one lesson, that if you don't know something and you ask ChatGPT to do it, then you have no way to check. So I'm trying to have the feeling of using AI, and it's still this feeling of grounded in them, and so that they will have also some remembering that this is where you can use it or not. So I have different types of questions, some that you can do just with AI, some you can do with the help of AI, and some you cannot do even with AI. And then I realized that there are several kinds of ways of using it. Some people just know what task they will ask ChatGPT or not. And some people will use it constantly and will just know the best prompt to do it. So I actually taught students also how to do proper prompt engineering. It, of course, constantly evolves, but these are all the skills I gave them. Proper prompt engineering skills, the capacity to know, the critique of being able to know when you can use it or you cannot use it, and then also being constructive, and also how you can collaborate with others and accelerate some of the workflow. So my takeaway would be learning how to use it responsibly through salient examples that will ground this feeling in them, not just saying it, like demonstrating it without even telling them what will happen beforehand. I really want them to realize, whoa, that's a lesson I will remember now in the future. So this is the approach I'm using, and I'm trying like all sorts of layers of how to use it.
Thank you. For me, I have some questions. In your first work, you mentioned that you're concatenating to the two modalities, the static images and the time series. Mm-hmm. But maybe I skipped. How did you do this? Because yeah, for the static images, you used a transformer to concatenate over time. But I skipped this. I skipped how to relate this with time series. This is the first part. And the second part, for your second work, you are using ensembling for time series. So you have several models, and you are using the mean or the average or something like this. Why aren't you using, for example, some probabilistic forecast intent to have a lookup about the uncertainty of the model, something like this? This is my second